Now, understanding the idea of conditional and unconditional default probability, because then when one studies credit ratings, it is very closely aligned with the idea of credit risk analytics. And for that purpose, connecting these ideas from a probability of default perspective makes a lot of sense, because then a lot of calculations which we do as a part of ratings can act as an input to our core credit risk analytics models. So let's understand these two important definitions. What do we mean by a conditional default probability versus what do we mean by an unconditional default probability? Now, below, if we observe, there is a table. Now, this is a kind of table which is published by rating agencies. And let's try to interpret what this table means. Because then if you see, there are many numbers which are here. We'll try to put some sense in these numbers. So we have the term which is in years, which is shown as the top column. And then we have the rating scale right from AAA up to CAA, which is the first column. And then we have all of these set of numbers. We'll understand how to interpret this. Now, for example, let's say we take a bond which is rated A. And these numbers which you're seeing, these are pertaining to the idea of probability of default. And we are trying to use it in order to extract what we call as conditional and unconditional defaults. So if I focus on a bond which is currently rated A, then if we look at year 1, we see the number as 0.051. So this means that bond which is currently rated A has a 0.051% chance of defaulting by the end of the first year. So that's this interpretation of 0.051. Let's say I want to expand this further and look at year 2. Similarly, I stick to the same bond. I see the year 2 number is 0.165%. How do we interpret this? So a bond which is currently rated A has a 0.165% probability of defaulting by the end of the second year. Similarly, we can do it for the third year, fourth year, and so on. So then we can go further. And if you'd like to understand what is the probability that this particular bond will default during the second year, because up till now, if you see point numbers 2 and 3 pointed out to the probability of the bond which is currently rated A to default at the end of the respective years, first or the second year. Let's say we are looking at understanding what is the probability of default during a second year. Yeah. So then in that case, we are going to use these two numbers. We'll focus on these two only. So now if you want to figure out what is the probability of a bond which is currently rated A to default during the second year, that is, we take a simple difference, 0.165% minus 0.051%, which is 0.114%. So this is the probability of defaulting during the second year. Now, empirically, if you see, there are 5 and 6, the point numbers 5 and 6 is something which you have seen in practice historically as well. So empirically, we have observed that investment grade debt generally have a probability of default which increases over a period of time, whereas junk grade bonds have a probability of default which decreases over a period of time. So that's something which we have empirically observed. Now, let's start to understand these two definitions as we have put in the title of this slide, unconditional versus conditional default. So let's look at the unconditional default probability first. And for this, let's use the bond which is rated CAA. So let's take a bond which is currently rated CAA. And we know that it has a probability. So if I take these two numbers, so if I want to estimate the probability of default during the third year, as we know, based on our earlier calculation, we simply take a difference. So the probability that a bond which is currently rated CAA will default during the third year is a subtraction of 38.682% minus 29.38, which is 9.29. Now, this is called as an unconditional default probability. Because then if you see, this is not conditioning on any information. We are using this data which is available and we are doing a plain and simple calculation. So effectively, we say that standing at time point 0, we see that 9.29% is the probability of default of a bond which is rated CAA during the third year. And this is what we call as an unconditional default probability. Now, let's try to expand on this analysis and try to understand what is a conditional default probability. Many times, reference books might call the conditional default also the words like hazard rate or default intensity. So these are synonymous terms which many books might use. Now, the first of you do is calculate the probability that the bond will survive until the end of year 2. So if you look at the year 2 number, which is 29.384. So now if I want to figure out what is the probability that the bond has survived until the end of year 2, I take a difference of 100% minus the default 29.384, which is 70.61%. Now, remember, we are interested in the conditional probability idea. When we say the conditional probability, that means we are going to condition our answer based on something, isn't it? So that will be our analysis. So think of it just like this. So when we say unconditional probability, we can think of a probability of some event A happening. Whereas if it's a conditional probability, we know the definition. It's probability of A given a certain event B which has happened. So now if you want to calculate the conditional probability of default during the third year, then we say that in our pursuit to calculate that, we will look at the probability that the bond has not defaulted prior to it. So the probability that the bond will default during the third year, conditioning on the fact that before that there has been no default, that is given by this ratio. So if you see, this 9.29% is what we had calculated above, which was the unconditional probability. And in the denominator, if you see, we have a 70.61%, isn't it? So this is exactly this same number. So effectively what the denominator says is it's conditioning on the fact that the bond has survived until the end of year 2. I.e., we are saying that we are trying to calculate the probability or the conditional probability of default during year 3, given the fact that the bond has not defaulted prior to that. And that comes out to be 13.71%. Now, conditional default probability at times also, as I mentioned, is called as the hazard rate. Now, as I mentioned, empirically we have observed the behavior of investment grade and the below investment grade bonds from a probability of default perspective. So if you look at the investment grade bond first, it is, as we mentioned, typically it is observed that the probability of default will tend to increase as a function of time. This is because there is a greater chance that the financial health of a good rated company might decline in the future, because at present they are very, very strong. But then a few years down the line, they may not remain that strong. So accordingly, their credit standing can weaken and their probability of default could increase. Whereas for bonds which are on a lower credit rating scale, generally the opposite is observed. That is, if these kind of below investment grade bonds are able to survive for the first couple of years, then there is a very good possibility that they are going to improve in their financial health going forward. So that's like a general observation which you have seen in the market over the years. Now, we had mentioned the word hazard rate on the previous slide. So let's try to do a little bit of maths in this, and we'll see how it can be used for making some useful analysis as well. So hazard rate, also called as default intensity, it is a measure of a conditional default probability. Now, typically these hazard rates get used as a part of it's an input which you use in what we call as the intensity models. Because then when we do credit risk modeling, there are two classifications of models which we generally study. In the latter part of today's discussion, we'll make a brief mention of the Merton's model or the KMV model, etc. All of these are what we call as structural form models. The other class of models is what we call as a default intensity or a hazard rate model. And that's why this idea of hazard rate plays a very important role. So as we know, default intensity or hazard rate is a measure of conditional default probability. So what question does the hazard rate tries to answer? It tries to answer what is the probability of default between time t to t plus delta t, given the fact that there is no default which has happened up till time t. And hazard rate can also be used to arrive at unconditional probability of default as well. So let's put in some maths and try to understand this. Now, let's say we call H bar as the average hazard rate between time 0 to time small t. Now, the unconditional probability of default between times 0 to t is given by 1 minus e raised to minus h bar into t. So naturally, as we know, probability of default plus probability of survival, they need to sum to 100%. And therefore, we can go further and say the probability of survival up to time t is given by e raised to minus h bar t. Now, these calculations can be worked out. So that way, if we can take a small time step over to t to t plus delta t, and then we can come to these results. But for now, we'll take these results as a given. So just to summarize quickly, probability of survival up till time t is e raised to minus h bar into t. And unconditional probability of default between 0 to t is 1 minus this number, 1 minus e raised to minus h bar t. Because as we mentioned, both of these need to sum to 100%, and that's how we can get this relation. Now, if we are interested in calculating what is the unconditional probability of default between times t1 and t2, so then it will be just a simple subtraction. So it can be given as this quantity. Now, let's say h1 bar and h2 bar are the hazard rates between today and two respective time points, t1 and t2. So think of it as like this. So we have 8 today, and let's say we have a t1 and we have 8 t2. And we say that these are the respective hazard rates for t1 and t2 respectively, standing at time 0. Now, let's say if we assume that the hazard rate is constant at 1% per year, then the probability of default at the end of third year can be given by this. So 1 minus e raised to minus h bar into t. T is equal to 3 years and h bar is 0.01. So that is 2.96%. Now, if you have to look at the unconditional probability of default occurring during the fourth year, recollect a similar calculation which we had done on the table on the earlier slide. We take a difference, isn't it? So it's e raised to minus h bar t. So the hazard rate of 1% is constant, but then we have 3 and 4, isn't it? So that comes out to be 0.966%. Now, if you want to figure out, so all of these were the unconditional numbers, isn't it? Now, if you want to calculate a conditional probability of default during the fourth year, given the fact that there has been no default until the end of the third year. So that's the idea of conditional default as we are aware. So then we take a simple ratio. So we take the probability or the unconditional probability of default during the fourth year, which is 0.966%, upon 1 minus 2.96, which is the probability of default by the end of third year. That is, we are assuming that no default has happened prior to the end of third year.